Hello. So this is word search. It's essentially a 2D matrix, and we need to find the word where each consecutive letter is connected to the previous one. So the question reads, given in a grid of characters and a string word, return true if the word exists in the grid. A word can be constructed from letters of sequentially adjacent cells where adjacent cells are horizontal or vertical. So up, right, left, and down on each letter. So essentially, this question is a recursive backtracking depth first search problem. So we need to go through this 2D matrix or 2D array, check each letter, and on each letter, we also need to check the surrounding. So there's the recursion. But if we don't see any connected letters for the next one that we need, like if we're on S, we're looking for E, we're going through each letter to start, we're looking for that first S. But what if we get to this S here? Then we need to recurse, check the sides. Oh, there's no E connected to this S here. So then we need to backtrack. And how do we do that? We need to essentially turn this S back into an S, because if we get to this S, we go to the next letter E, we're looking for the next letter, but if we're looking up, we don't want to mistake this letter that we've already visited for the next letter that we're looking for. So there's a couple parts to this question. We need to track which is visited. We also need to tell it which corners to recurse and run the backtracking function again. So left, up, right, and down. We also need to make sure that we're not looking on out of bounds areas, and down and left. So the main loop is going to look for that first character, and then when it finds that first character, it's going to run the backtracking function on S, which is the first letter in that word. So for example, here we're looking for A, B, C, C, E, D. So A, we're looking for the next letter in the word, which is B. So then we move over to here. Now we're checking all the sides again. We're looking for C. We have to change this A to like a pound symbol or any character that isn't a letter. And then if we don't find that next letter, we need to switch this back to the actual letter. So maybe in this example here, we have to keep this S and S, because what if the end of this word, S-E-E-D-A, what if we needed that S again? So that's why we have to change it back to the letter. So this has two main parts, and I'm going to try to do this in one shot before my computer overheats. So there's the back function, which will take the space that we're on, the character, I and J for row and column, and then the actual letter in the word that we're on. So we'll come back to this. And the next part, or the main part of this function, is a loop, nested loop, to run the first character search. And then it runs through the whole matrix, da 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 da, to the end, looking for that S. And then once it finds the S, then it runs all the recursion. So it checks all the sides once it finds the S. But if we don't find this first character, then there's no point of checking anything. So for I in range of length of the board, so this is checking the rows, because a 2D array is essentially an array of arrays. So there's your first row, here's your second. So the length of this board is going to be how many how many rows there are. See, you're essentially checking the length of this array here. And then inside this, we need to check the columns. So for range, in range of the length of the board, but we're only looking at that first item. So the length of this will essentially tell us how many columns, and this is kind of assuming that you're not going to have an odd number, like it's a uniform constraint. So all the rows and columns should be filled out, if you know what I mean. So this will check how many columns there are, assuming that there's 1, 2, 3, 4. If we look and all of the rows are the same columns. So inside this, if this back function that we make returns the first character and it runs through the recursion, then we can return true. So this 0 here essentially is looking for that 0 index of the word, so the S here. So you're just running through the whole thing one time to get that first S first. And then inside this back function, maybe we should call this backtrack. Inside this backtrack function, then it runs everything, checks the boundaries, sets the S to visited and all this, but we'll do that later. And then if none of this goes through, then the word is not in this matrix, so we return false after this. So the main meat of this problem is this backtrack function. So inside this, we need to check the K. So essentially, if this K, and K is like the letter inside of the word, so there's 0, 1, 2. So if we get to 3, or the third letter, which is 0, 1, 2, if we get to this K where we're at the end of the word and this length is equal to the K that we're on, we know that we're done with this whole thing and we can return true because we found the word in the matrix. So if the word K, so the letter that we're on, is equal to the length of the word, we can return true. So if the letter we're on, actually no, that's wrong. If K, when we increment this, if that K is equal to the length of the word, then we return true. Now we have some boundaries. So we need to check that we're not looking here, we're not looking here, and we're not looking here, outside the boundaries. And we're also checking if this letter is the thing we're looking for. And we're also doing an edge case where maybe there's no rows and no columns. So if, and we can put all of these in one block, and if these happen, we're returning false. But inside here, we can put everything together. So if there are no rows, if I is less than 0, or j is less than 0, there's no rows, there's no columns, or we're outside the boundaries, so I is greater than the length of the board. So if we're down here, if we get down here, we're not looking here, it's greater than the length of the board. And the same for the columns. If j is greater than the length of the board, then the columns inside the board. So if we're outside of the column boundaries. And the last one is for the letter. So if the letter we're on, K, is not equal to the board, the actual index of the iteration that we're on, J. So if the letter we're on is not even the letter, like we get to A, this is going to fail because this A is not S. We're looking for this S. So this will return false. But what about if we get to this S, which is what we want? We want the S. But what if we get down here? Let me back up. If we get down here, we go through all these, we get to S. We're looking for this S, but what if we get to this S? We check all these sides, but we don't see the next letter. So we need to set this back to S, because in a successful iteration of this whole word, we need to set these to visited so we don't check them again. So we can make a temporary variable of the iteration that we're on, and then set the board, whatever we're looking at, the letter, to visited. And by this, we can just put whatever we want. We could put just gibberish, because we're just checking later. Is that the letter? Oh, no, it's not, because we set it to this character or whatever. And then here is the main recursion part. So essentially what we're doing is we're going to call this backtracking function again inside of the backtracking function that we call here. Once it hits this first character, then it just jumps back and forth between this whole logic set. So if, and we can put all this in a block, and if this is successful, we can return true. So the way we do this is for checking recursion, for checking the 4 sides. So here we have, we're going to call the backtrack with I, J, K. And we're checking 4 of these sides. So we need to copy this. Get rid of this one. So how do we know what is up, left, down, and right? We're still recording. We're not on fire. That's good. So we get to this first letter S. Say we're here. We need to check up. So up is just I minus 1, because here's row 0, 1, 2. So we're on row 1. We need to check row 0 above it. So it's I minus 1. So just take that J position and go up 1. So that'll check E. And then we'll do that for the 4 corners. So there's up. See, I'm lagging, so we're getting slow. I got to finish this quick. This is down. So if we increase the row, that'll be down. And left is -1 on the J, +1 on the J. This is left. This is right. So inside this recursion function, we're calling backtrack again, but we also need to, we check the sides, but we're on S, we need to check the next letter. So we need to, each time we need to increment to the next letter in the word. So this is represented by k plus 1. And that can be for everyone because we're checking for the next letter up, next letter right, next letter down, next letter left. And then the last part is I talked about setting the visited. So this S is technically now a percent sign or a money sign. Because when we're on E and we're looking for E, we're checking up, but we don't want to check that because the word doesn't go backwards. And that's the backtracking. Well, technically not backtracking. Backtracking is when this S is reset and we go back to the start to look for the first S. But essentially this is visited. We don't want to look there, is what I'm trying to say, brother. So if all this goes through, we'll return true because we get to the end of the word. It calls itself on itself. It checks the letter here. It sets it to visited, checks all the corners, and then it checks itself again on the next letter. So if that doesn't go through, then we need to, like if we get to S, we need to set that S back to S because we set it to this. So we need to set the board, set back to normal letter. So the board I, J, we need to set it back to the original letter. We stored S here, for example. S original. So we set that back to the S, and therefore we would return false in this situation because we didn't find that first S. And I think that's the logic. So before I just ape into the run button, we're going to just run through this. So we're checking the K. If K got incremented to the length of the word, that means everything went through. We're checking the boundaries, columns, lengths. We're actually checking the letter, returning false if it hits that. So if we're in bounds, then we need to set that letter to something. Then we backtrack on it, up, down, left, right, with the next letter on everything. If that doesn't go, then we need to set that letter back to something because we set it here, and therefore false. And this is the main loop that runs everything. So this is just looking for that first index in the word S. Let's see. Comparison. Invalid syntax. Maybe you meant instead of line 6. Oh yeah, comparison. If word K why am I doing that? Okay, if the word, letter, blah, blah, blah is not what we're on, $37. Another bracket. Yeah, boys! So there's the answer, lads. And let's check the test cases. because they like to put these annoying test cases. Even though it is accepted, it might not pass because they like to cause you trouble. So that is the solution to this. I actually got asked this on an interview and I totally bombed it, so that's why I'm making this video. So anyway, thanks for watching.